Okay, so today's topic of discussion is spacecraft thermal control. So today I'm going to talk about basically how the temperature of a spacecraft is maintained within specified temperature limits while it is operating in a harsh space environment. So with the course of this webinar, I'll take you through what is the agenda of today's discussion. First, I'll introduce you with the spacecraft configurations. Then why thermal control of a spacecraft is needed. Then the what is the thermal design philosophy when it comes to different space missions like satellite mission or a lunar landing mission. Then I'll talk about how we implement this basic design philosophy using commercial softwares and analyze the thermal performance of the satellite. Then I'll briefly take talk about the thermal loads that Chandrayaan-2 has faced during its journey from Earth to Moon, which will be a small case study. And then I'll take you through what is the present state of the art in the thermal control design. So, state of the art basically what is the present technology readiness level we have in terms of thermal design. Then I'll talk about what are the career paths and the job opportunities in this field. Okay, so while we proceed to understand how the spacecraft thermal control is done, first I would like you to understand what are the spacecraft configurations. So spacecraft can be a spin stabilized or a three axis stabilized. So before that, let's understand because there's some confusion about spacecraft and a satellite. So spacecraft is any vehicle which is designed to operate outside Earth's atmosphere. But a satellite is a spacecraft, but reverse is not always true. You see, depending upon the mission, for example, ISS, International Space Station, it's a satellite, it's a spacecraft. But on the other hand, there's a lunar lander like Chandrayaan-2. It's not a satellite because it's not orbiting any. Its mission is not to orbit any planet, and it will eventually land and do perform its mission. So now there's a configurations in the spacecraft. One is spin stabilized, which actually the difference is that the spin stabilized satellites stabilizes themselves by spinning about its vertical axis, just like a gyroscope. It works on the principle of gyroscope. Secondly, there are three axis stabilized satellites, which means these are the most common one these days because they have a mechanism to control the attitude of the spacecraft using the thrusters or the reaction wheels. So both have their advantages and disadvantages. So for the spin stabilized satellites, since it is rotating continuously, there need to be a d-spin movement for the antenna to point at a certain point towards the Earth, which is not possible, which is very difficult actually to in a spin stabilized satellite. But for the three-axis stabilized system, it is it can be controlled. The attitude can be controlled through the reaction control system of the satellite. Now, a spacecraft is generally referred in terms of a bus or a platform. Bus of a platform or a platform, it consists of various subsystems which helps operating the spacecraft for its mission. Now, for a specific mission, there is a specific payload. For example, if there is a communication satellite, there will be a payloads specified for the particular communication system. Or if there is a earth observing satellite, then there will be a camera kind of payload on the spacecraft. So here I'll list down the what are the basic spacecraft subsystems. Now there are many subsystems of the spacecraft. which are essential to perform the spacecraft operations. First of them comes the structures, which is the physical structure of the spacecraft where all the subsystems are mounted. So now this structure is generally very light and made of composite. For example, the panels of the structure, they are made of honeycomb sandwich panels, which are ultra light and very strong. Then the electrical power systems, generally called as EPS. It is used to generate and distribute the electrical power to the spacecraft. So it consists of solar arrays, batteries, your power distribution units, your electrical harness. Now, power distribution unit comes into the picture where you have to distribute the power at different voltages to different components of the spacecraft. So there are heat losses in that particular unit, power distribution unit. Then comes your telemetry and telecommand system. So telemetry and telecommand system is basically the data inlet and data outlet of the spacecraft. So it comprises of the electronics which deals with the communication of the spacecraft with the ground. So basically all the spacecraft operates in a certain frequency, the X band or the S band. So the electronics related to this system comes under telemetry and telecommand. Then we have guidance, navigation and control. So at any certain point when a spacecraft is in the mission, its position, its attitude needs to be known. How it is done? It is done using the inertial movements, initial measurement units. Then we have star sensors, sun sensors, due to which helps in getting all the data from these sensors and pinpoint the precise location of the spacecraft. Then we have command and data handling. So basically, this is related to the electronics, which is the brain of the spacecraft, meaning the onboard computers where all the your flight softwares are placed. Then we have propulsion system. So propulsion system is basically the your thrusters, your tanks mounted on the spacecraft, your plumb lines, your gas lines are consist of the propulsion subsystem. Then the thermal control. So thermal control consists of various thermal control elements like multilayer insulation, optical solar reflectors, then thermal interface materials, and there are so many things we will discuss further. Okay, so now with this spacecraft subsystems, these subsystems needs to be operated at a specific temperature range. Now to achieve this specific temperature range, we need to have a thermal control because the space environment is very harsh. You must be knowing that the space temperature, deep space temperature is 4 Kelvin, that is minus 269 degrees Celsius. So there is no component that will survive, or a spacecraft won't be able to operate efficiently if temperature goes this low. So we need a thermal control. Now we also know that there's only two modes of heat transfer in spacecraft, a conduction and a radiation mode. Since due to the vacuum environment, there is no heat transfer due to convection because of presence of no fluid, and there will be a huge temperature gradients if let's say one component is getting heat transferred through conduction, and the other component just adjacent to it is looking at the sun. So there will be a huge temperature gradient. So to remove these kind of gradients, we need to have a thermal control. Then again, when your spacecraft is moving for a certain mission, there are times when it is in the shadow of the earth. Also, if there's a moon landing mission, then there are reasons. for example on the South Pole, which are not illuminated. So spacecraft lose the heat to the environment at very drastic rate. Then we have a engine wall temperatures, which is around 1400 degrees Celsius. Now these engines will fire when you have to do the any orbit raising or orbit lowering maneuvers, or you have to adjust the attitude of the spacecraft. So for example, you must have heard about the Chandrayaan 2, that it has to take a lot of rounds in the orbit. So to reach a specific orbit, it has to raise the orbit. How it is done? It is done using the thrusters. And while using these thrusters, there will be a increase in uh, temperature of the surroundings of the spacecraft. So to protect the temperatures, to protect the heat transfer from the wall engine wall to the components, we need a thermal control strategy. Now, this is a specific case for the lunar missions. When the spacecraft reaches the lunar orbits, there's a point called a subsolar point where your spacecraft can be in between your sun and the moon. So if you know the flux of the moon, which is reflected from the moon surface, is equivalent to 1296 watts per meter square, whereas the solar flux is on average is 1367 watts per meter square. So when you are at this position between sun and the moon, your spacecraft essentially face the two different sun from either sides. So then it has become imperative to have a thermal control because spacecraft is now at very high temperature. Now, before moving to how what are the control elements, we'll see how a thermal subsystem design cycle works. So first we have a thermal design and analysis. So design is proceeded, it's based on certain requirements. There are certain level of requirements called mission level requirements, system level requirements, and then comes the subsystem level requirements. In the subsystem level requirements, there are requirements for every subsystem, like I mentioned, structures, EPS, propulsion. So similarly for the thermal, there are requirements. For example, the first and foremost requirement is that the spacecraft must operate within a specified temperature limits throughout its mission life. Then there are thermal, we need to analyze the thermal environment. Once your mission level requirements are set, you know what is the environment which a spacecraft is going to face during the mission. So you have to analyze that. Then there is a thermal design philosophy. So depending upon the mission type, let's say you have a satellite mission, a low Earth orbit mission, or a lunar landing mission, or any interstellar mission. So there's a design philosophy, which we'll discuss in the later stage, based on which design is evolved. Then, based on this design, you implement this design and analyze it using certain commercial software or tools. And after your design requirements are satisfied through this analysis on the situation, you reach to a level where you can define the mass budget depending upon uh, means you will be contacting two vendors and you will get to know what kind of mass budget you are looking at. So typically for a low earth orbit satellites, the mass budget of a thermal subsystem is around 6% of the dry weight of the spacecraft. So the next part comes is the thermal implementation, where you have to define the bill of material based on your mass budget. Then what is the thermal hardware you have to procure if it is commercial of the shelf, what you have to fabricate, and you have to create the implementation process documents. Then comes the features for the quality assurance and quality control. Now, quality assurance and quality control is very important in any space project because it involves huge amount of cost and time. And if it's a manned mission, then there's a risk to human life as well. So QC/QA helps in ensuring that team building the spacecraft does the work it should be done, which means the correct material is available to the team and they are following the right step. So, but how do you ensure that? You make a documents, you document each and every steps which is followed based on the documents which are already available, which are process and procedure documents during the production of the spacecraft. So, for example, if you are installing a thermal sensor or a thermocouple on a spacecraft, there's a process document which lists how you are going to install the thermal sensor right from right from cleaning the surface of the spacecraft, what is the procedure, how you have to insulate that area first, then you have to take that thermal sensor and use the captain tape to stick it on the particular surface. So like that, there's a whole procedure document. So that's how you assure the quality of the spacecraft. Then thermal testing. So thermal testing is basically done at multiple levels. So it will be done at unit level. It will be done at spacecraft level. So by unit level, I mean, for example, there is a avionic box which needs to be tested. So this avionic box, it's a complete unit. So tests will be done on this unit alone and verify it. Then there are material acceptance tests. For example, you are procuring a raw material for a multi-layer insulation. So you need to verify it is able to the material properties are well in what you need to be in design. For example, if you are procuring a aluminium plate, so you need to ensure the conductivity of the aluminium, the density, the grade of the aluminum are right for your design. Then you do there are property measurement tests. For example, the radiators or the surface finishes of the spacecraft or the paints. You need to ensure they are having the right emissivity and absorptivity. Then there are implementation tests. For example, you need to measure the conductance of the multi-layer insulation, whether it's giving you right insulating performance or not. So this is how a thermal design cycle for a spacecraft works. So now we'll go and see how a thermal control, what are the thermal control elements which are used for the spacecraft thermal design. First of all, is the multi-layer insulation. I think a lot of you must have seen it in on the internet or on TV. You have seen that there's a gold film in which a spacecraft is wrapped. So we always wonder what is this gold? Is it really a gold film? So let me tell you, this is a multi-layer insulation which is made of multiple layers of polyamide or polyester thin sheet. So if you see this picture over here, it have mylar sheets which have a vapor deposited aluminium on both the sides. Then there is a layer of net which is made of Dacron. So first there is a layer of this aluminized mylar sheet. Then there is a Dacron netting, and then again there is a aluminized sheets. Now the purpose of having this kind of arrangement is when this Dacron netting is in between, the only mode of heat transfer between the two aluminized sheet is the radiation. So the multi-layer insulation, depending upon what kind of conductance you need, the insulation the number of layers on the multi-layer insulation can vary from 5 to 30. Now, if you see this, the topmost layer, which looks like a gold, it is actually a Kapton tape, one side of which is having a vapor deposited aluminium. That's why it gets its color like a gold. So Kapton is basically yellow, and aluminium is a shiny surface, having a shiny surface. So that's why it looks like a gold. So this is the important component of all the spacecrafts, of all the satellites normally. Now multi-layer insulation serve other purposes as well, like protection from the debris in the space environment, which for which sometimes fiber cloths are also used as a last layer of this multi-layer insulation. Second comes the optical solar reflectors. Now optical solar reflectors are basically the quartz below which your silver is plated. If you see image 3, here you see these thin tiles, which is basically quartz coated with silver. Now, how this optical solar reflector work is, it have a high emissivity in IR spectrum and very low solar absorptance. So we'll talk about it. What are the how it works when we come to the thermal design philosophy. Now, thermal paints and heaters. So thermal paints are basically they can be conductive, electrically conductive, and non-conductive also. And these paints basically help in optimizing the surface optical properties of the spacecraft. For example, if let's take aluminium, a polished aluminium have a very low emissivity. It's around 0.03. But if I paint this aluminium, the emissivity becomes more than zero point 0.9, which means I'm able to radiate more heat from the spacecraft. Then there are the thermal interface materials. So thermal interface materials helps in increasing the contact conductance between the interfaces. Some gels, some silicon pads, they are used as interface materials, and this actually fills the small deformities between the two interfaces, which is not seen by a naked eye, and increases the contact conductance between the interface, and thereby it increases the heat transfer rate. Then thermal sensors are the essential part of the thermal control system, because they gives us the feedback on how to control the heaters plus monitor the health of the spacecraft. Now there are many types of temperature sensors. They can be thermocouple, they can be thermistors, and thermistors are also of two types, PTC and NTC, negative thermal coefficient or positive thermal coefficients. Now depending, they have a different ranges and accuracies, so depending upon the requirement. For example, if you are putting a thermal sensor outside of the spacecraft which is exposed to the space environment, you normally use PTCs or PRTs, which generally have very high accuracy and very high temperature range. For internal of the spacecraft, you mostly use negative thermal coefficient thermistors. And for the testing purpose, mainly thermocouples are used due to their ease of installation and getting the data. Then comes the heaters. So these heaters are the heaters also comes in different varieties for the spacecraft. They could be a foil heaters like the one you see on the figure 2. So these heaters have just they have a pressure sensitive adhesive. You just take off the thin film of them and you can just simply paste on the spacecraft. Then there are other kind of heaters also which are called tape heaters. You can roll those kind of heaters on the plumb lines which carries the propellant from tanks to the thrusters, because sometimes it is required to maintain the temperature of the plumb lines also. Then there are heat pipes. So heat pipes like the one you see on the figure 4, this is a loop heat pipe. So basically it carries the heat from the high temperature source component to the radiator, and then again they are basically the two phase. They have a heat transfer using two phase. So there is a liquid which carries the heat and turns into a vapor, and it uh, goes from high temperature source to the sink, which is the radiator, and then condense over there, and then liquid again return to the high temperature source. So this is the loop heat pipes. There are other heat pipes also which are used in your laptops also. They are closed loop, sorry, they are constant conductance heat pipes and variable conductance heat pipes also, which are used in your laptop also. They have a very high thermal conductivity, thermal conductance, which is around 10,000 watts per meter. Then we have thermal straps. Thermal straps are basically, these are the flexible straps which are used to transport heat from one place to, or one component to the structure to dissipate the heat in the structures. Then we have heat switch. So heat switch, how they function is basically they are mounted between the interfaces. Now, depending upon the whether you want to reject the heat or you want to get the heat from the other component, there is a heat switch, basically a bellow kind of a structure which get elongated if you want the heat to get inside, or they can be detached from the other interface if you don't want the heat loop to be complete. Okay, now we know the what are the thermal control elements which are used for the spacecraft. So I'll take you through the what is the general design philosophy for the spacecraft or any satellite. Now, the first and foremost in this is to insulate the spacecraft to reduce the temperature fluctuations caused by the environmental conditions. Now, what happens, as we know, while the spacecraft is in deep space, one side can be seeing the sun and another side can be at the can be in the shadow. So one side is getting the heat from the sun and other side is rejecting the space heat to the space. So what happens? This insulation, the multi-layer insulation, it works in both ways. It neither allows the heat from the sun side to get inside the spacecraft, nor it allows the excess heat, which is the heat from the inside the spacecraft, to leave from the other end, which is on the shadow side of the spacecraft. So basically, your spacecraft is now an isolated system which have its own thermal control, and you can control its temperature very well. Then you need to reject if there is some excess heat in the system. So for that we use OSRs, which is optical solar reflectors, also called radiators. Now these radiators, like I said, they have a high emissivity in IR spectrum and low solar absorptance. So let's say if your sun is having a flux your spacecraft is receiving the solar flux at the rate of 1000 watts per meter square. So with the 1 meter square of your radiator, your solar flux will reduce to only 20% because your solar absorptance is normally less than zero point 0.2. So instead of 1000 watts per meter square, you'll only be receiving 200 watts per meter square, which is being absorbed by the spacecraft. Other than this, if there is a internal unit which is dissipating the heat from the component, you can just mount this unit under the panel where this radiator is placed so that it can dissipate the heat to the environment. So now the advantages become twofold. First of all, you are receiving less heat from the environment, and secondly, you are radiating more heat to the environment. Then we can use the heat sinks which have high heat flux, and basically they are used to spread the heat across the structure of the spacecraft. So if we have a component or a dissipating component, let's say for example electronics for a communication system which normally dissipates more heat and very less efficient, we can use a aluminum plate between the structure and this heat source, so as it can dissipate the heat through this plate and spread it over the spacecraft, which actually helps in reducing the thermal gradient across this component also. Now as we talk about the engine firing during the maneuvers of the spacecraft, we know we have to protect the spacecraft from the high wall temperatures of the engine, because there are components which are normally mounted on the lower deck of the spacecraft which means, and there are very sensitive components like the imaging systems, for example the sun sensors or the star sensor. They basically have a, a image sensor. Now if they are working at very high temperature, the image could be very noisy and it won't be able to perform very well its operation. So for that, sometimes the spacecraft we use heat shields. They are mostly made of titanium. Titanium have a low thermal conductivity and low emissivity as well. So depending upon how much you want to shield the spacecraft from these walls, what is the requirement, you can use number of layers of these titanium sheets which are separated using a ceramic beads. Now you need to maintain the temperature of some components which are on the shadow side because they'll be still running very low on temperature. So now for that you need a feedback system, basically a thermostat in which you can set the cut off and cut in temperatures for the component. Say if, let's say, battery is one of the most important component which operates in very narrow range, around 5 to 20 degrees Celsius. You have to keep the battery in this range for a maximum performance. So there are sensors and heaters on the battery which ensures that if the temperature falls below 5 degree, the heater will automatically kick in, and if the temperature reaches above 20 degree, this heater will cut off. Now these heaters also have some redundancy, meaning there could be two heaters. Essentially there are two heaters overlapping each other, and in case one of the heater fails, there is other heater to take care of the component so that it will be in the operating temperature limits at all the time.